So this video is all about forces on ramps. Basically, why do things go down hills, right? And what are the numbers that kind of cause that acceleration when you put something on a hill and it starts to slide down it. So the idea here is, first, we've got this block sitting on a hill, and we know that the weight of this object acts vertically, right? That gravitational force is going to go in this direction. But the direction the block wants to accelerate is this way. So the question becomes, how is that possible? Where's that net force come from if the only force really acting on the block is gravity pulling it straight down? Well, what we can do is we can split that weight into its two components. Okay, we have a part, just like we've done with velocity. Okay, we can determine the two components that are going to be based on the angle of the ramp. So what gravity is really doing is two things. One, it's going to push on this axis that is parallel to the ramp. And it's also going to push on this axis that is perpendicular to the hill that it's acting on. Okay, and we can break it down just like we did with velocity going onto each axis. We'll do the same thing here with our forces. So we'll go over to that vertical, that perpendicular axis, and get that force going this way. And this is going to be the force of gravity that's actually pushing into the ramp. Okay, so part of that weight, okay, we have that weight here. Part of that weight is going to be a force that's driving the block into the hill, making sure it doesn't come off the hill. The second thing that's going to happen is we can go up here to the horizontal axis and that parallel axis, and then we have this orange force here. That is going to be the force driving the block down the ramp. Okay, so we have these two components, an F in and an F down, of the weight. They add together to equal the weight, but they're the two things that are going to drive the motion of this object when we're at this angle. So the force going into the ramp is going to be balanced out by the normal force between the block and the ramp. So this should have the exact same magnitude and be in the exact opposite direction, remembering that the normal force is always perpendicular to the surface. And then this F down here is going to be influenced by how much friction there is between the two surfaces. So there's the force of friction right there. Okay. Now, since F sub n and F in balance each other out, the key for the net force then is going to be the difference between F down and F sub F. So F net is going to equal F down plus the force of friction. Okay, but remembering that one of these two is going to be negative, right? F down maybe set that to be positive, F sub F will be friction. So the difference between those two is going to generate that net force, which is what's going to drive that acceleration going down the ramp. So what we want to do to actually find the magnitude of these forces. So let's look at this right here. First, we want to draw in the triangle. That's going to be show our two components, F in and F down. So let's go with our horizontal axis there, our perpendicular axis here. F in, of course, we're going to go over to this line. And this component here is going to be our force going into the ramp. And we go up to the axis here. And this force right here is going to be our force going down the ramp. Okay. And again, those are the two components of the weight. There's our weight down there. That's 100 newtons. And it's split into a force pushing it into the ramp and a force going down the ramp. Now, a couple quick notes. This is a rectangle, so F down is also over on this side right here. And the other thing to note is that this angle theta is the exact same as this angle right here. It is also a theta that we'd be measuring there. Okay? If you want to get into the geometric proof of that later, we can do that. If you don't care, that's fine too. But that is the same angle in measurement right there. Okay, great. Now we got that. Now we want to use theta to find F in and F down using our trig functions. Okay, so we can start with F in. Okay, and F in is the side that is adjacent to the angle theta, right? So adjacent comes from cosine. So again, cosine of an angle is equal to the adjacent, which is F in, over the hypotenuse. In this case, again, the hypotenuse is weight. So F in equals weight times the cosine of theta. Okay. The other one is F down. So F down is the opposite side. So an opposite side comes from sine of theta, and sine of theta is going to be the opposite side, which is the force going down the ramp, and that's divided by the weight of the object. That's our hypotenuse. So F down is equal to weight times the sine of theta. So if we want to know the magnitude of these two forces, we have our functions now. We have Fn equals weight cosine theta, and F down equals weight sine theta. Okay. Without friction, the net force on the block is F down. Okay. Sorry, I'm going to erase those lines real quick. Without friction, the net force on this block would be F down, right? Because Fn is going to be canceled out by the normal force going straight up. However, if we know something about the motion of the object, we can figure out how much friction there is, right? What F of F might be, or what the acceleration of the object be if we know the force of friction. Okay? The combination, again, of these two forces, okay, is what's going to determine the net force that's acting on the block. Okay, so let's apply this all to a sample problem with some actual numbers in it, see how it all plays out when we work something out. So in this case, we have a 20 kilogram block placed on a 15-degree ramp. So we're going to label this 15 degrees, okay? And it's going to accelerate this way at 0.50 meters per second squared. That's our A value. We want to know how much friction is there between the block and the ramp. Well, since we know we're accelerating in this direction, we know we have an F net in this direction. We also know it's a block on a ramp. We know gravity is acting on it, so we're going to have a weight pulling it down. We also know that we're going to have some kind of friction pulling it back in this direction. We also know that F net is going down, and we can split that gravitational force, that weight, into an F down. Now we know we have an F in as well we can split our weight into, but it's not going to be necessary for this problem because, well, F in is completely canceled out by the normal force, right? Those are balanced out. We don't need to worry about them. So the only things we really need to worry about are F net, F down, and F sub F. And we know that F net is just the sum of all the forces acting on the object. The normal force and the Fn cancel each other out. So the only forces left are the force of friction plus the force going down the ramp. So if we solve this for F sub F, okay, we're going to find out that that's F net minus the force going down the ramp. Okay, so the two things we need to find are what are the net force and what is the force going down the ramp. Well, net force is pretty easy. Net force is just m times a. It's Newton's second law. Okay, what is the net force acting on the object? Well, that's its mass times the rate of acceleration. In this case, the mass is 20 kilograms. The rate of acceleration is 0.50 meters per second squared. And that means that we have a net force of 10 newtons pushing the block down the ramp. So that means a combination of friction and the force pulling it down results in just 10 newtons worth of net force acting on that block. Okay, so what is F down? Let's find it out. So F down, again, based on what we've done previously, F down, remember that's the opposite side of our triangle down here, this one right here. So F down is going to be that hypotenuse, which is the weight, times the sine of theta. Okay. So one thing we need to know before we do that, though, is what is our weight? Remember, we were given a mass, we weren't given a weight. So to get a weight, we're going to do m times g, or 20 kilograms times 10 meters per second squared, or 200 newtons is our weight. Okay. So now we can go back and find F down by putting our 200 newtons in as our weight and multiplying that by the sine of 15 degrees. And we do that, we find out the component of the force driving the block down the ramp is 52 newtons. So we have 52 newtons worth of force acting on the block, pulling it down the hill. we only have 10 newtons worth of net force acting on the block, so now we have to figure out how much friction there is between the two surfaces, and it's just going to be the difference between those two. F sub F is F net minus F down from up above, so F net is 10 newtons, F down is 52 newtons, so that tells me there are negative 42 newtons worth of friction between the two surfaces. Okay? The negative simply tells me direction. We set the positive direction to be going down the hill. We set the negative direction to be going up the hill. So the amount of friction between this block and this ramp is 42 newtons as this block slides down the ramp. So we'll manipulate that and play with different situations in terms of whether or not we have the amount of friction. Maybe we're pushing on the ramp too, so we're adding in extra forces. Okay? But the idea here is the same, that we're looking at figuring out what the net force is. It's the sum of all the forces acting along the ramp surface.